So as the upper left-hand quarter is alluding to, this is a trickier question, and there are some common pitfalls that come out of this that we've got to watch out for. So it does tend to show up in both the homework and on exams because it really tests, do you understand the method that you're working with and not just lucking through and doing the division, okay, or the multiplication, whatever the case may be. Okay, so our setup, what do we want as a final answer? Inches. Cubed.
Cubic inches.
Or cubic inches. You're officially right.
Sorry,
No.
I'm slow on that one.
Okay. What do we start with? We've got our cubic centimeters, and we can drop in our number if we so chose. Now what we would go through and do is do our conversion. And what we would hope for, as with all of our problems, we would hope that I can get rid of centimeters, or cubic centimeters, and cubic inches in one fell swoop. Okay? So do I have a conversion factor between inches cubed and centimeters cubed? There is no unit. If we look at the information given to us, that is 1 inch is 2.54 centimeters. That is not inches cubed or centimeters cubed. That conversion factor is not given to us. Okay? There are a variety of ways that we can get to that appropriate unit or that appropriate conversion. And we'll look at those two methods here. So the first method I would go through and do, say I don't have that directly, but I do have a relationship between inches and centimeters. Okay, so what is that relationship? What is 1 inch? What number shows up? Let's keep trying. 1. Where should I put the 1? In front of inches. Why in front of inches? Because I could even accept that one. If we look at our unit, where does the 1 show up? It shows up in front of inches. It shows up on top here. The 2.54 also shows up in top in our conversion, okay, or in that equality. So saying it shows up on top in our calculation is meaningless, okay, because it shows up in top in our equality to begin with. Okay, what we want to do is place the number in front of the unit it's associated with. So the 1 shows up in front of inches, which means I write 1 in front of inches, which happens to be on top. Okay, you're right, it is still 1 inch. Where should I write the 2.54? In front of the centimeters. Okay. So let's go through and evaluate what this single calculation means. So let's go say we entered this into the calculator as is. We take the 498 and we divide it by the 2.54, which is some number that I don't know. But what happens to our units? 1 centimeter cancels with 1 centimeter, and this becomes a 2. The units that I end up with as an answer would then be, is that cubic inches? No, I have that extra centimeter unit in there, so I'm missing something. I need to cancel it, and I need to get more inches back. So what can I do? I can do the calculation again. Now what happens? Centimeter cancels, and I get rid of yet another centimeter. What would my units then again be? Our square inches times centimeters. Is that cubic inches? Still no. So what do I have to do? I have to do the calculation again. Cancel the last one. And now when I go through and do my calculation, I can take 498 divided by 2.54, divided by 2.54, divided by 2.54, and I should get the number that my calculator spits out, which we'll also address in a second. In theory, I can't read it on that screen, 30.3898 with our cubic inches. Okay? So the first trap is just doing it once, the 2.54, and saying, oh, that works. Well, some of you will say, well, isn't dividing by 2.54 the same as just dividing by the 2.54 cubed? Yeah, it is. Here's the second place on how this calculation usually gets bungled. You go through and you put that in there and you say, oh, the units don't cancel out right, so let me fix that. Units cancel out right. Now it's perfect. I still get the wrong answer. Okay. That cube that we put in there applies not just to the unit, but also to the number associated with that unit, which means I also have to do 1 cubed and 2.54 cubed. Now the units check, everything works out, and I get the correct answer. However you decide to do this, breaking it down into all of those individual steps to make sure all of your units convert, or you skip to doing the cubing, is up to you. Just realize it is very, very easy to make the mistake of not cubing the number as well as the unit. Right? Questions on that? This is why it's a big trap question. So let's go back to our answer. We have to be careful with our answer. If we entered this into our answer box, we would be wrong. Why? We have to track our sig figs. So we can go back to all of our conversions. I just heard that I hate sig figs. I agree with you. We look at our first conversion factor. How many sig figs in that conversion factor? Infinite. This was an infinite one. This was in the footnote of that English to metric conversion. 1 inch has been defined as 2.54 centimeters. That is an infinite amount of sig figs.
So technically, we're already using a metric system. If our numbers look based off the numbers.
In a very backwards way, I can see I can do that. Yeah.
Just switch.
And then in our first number, how many sig figs?
3.
3. That was actually kind of nice because we don't have to worry about any zeros. Because we got 3 sig figs, which means our answer needs to be 3. So we start at our left and start underlining our sig figs. There's 1, there's 2, there's 3. Our first insignificant digit, what's its relationship to 5? Greater than or equal to 5, so what do I do? Add 1 to the previous number, and I end up with my final answer being 30.4 cubic inches. Okay? Questions? If you've got issues entering it into the calculator, please let me know. You can talk to me after class, and we can work through that and make sure that you can get that correctly. Yes?
My way of thinking was doing 2.54 to the cube, like in your calculator, getting that answer, and then
That
dividing
works.
them.
It'll do the same thing.
You have 30, you get 30.36. Will there ever be like an instant where it's like 30.4 and then you don't round it and get it wrong?
I don't follow.
Like in a different problem. Like would it ever like not equal? I don't know.
So you will always have to track your sig figs, and you always have to track your rounding, regardless of the problem. So depending on what that first insignificant digit is, if it's less than 5, you leave it as 30.3. If it's 5 or bigger, you make it 30.4. If you go through and do the maybe this is where it's coming from. If you do the 2.54 calculation first, can you give me what that number was?
30.365.
That was just the 2.54?
That's wrong.
It was 16.38.
I was going to say,
16.3.
yeah. 16 point numbers?
387.
Just 387?
064.
Just 064?
16.387.
So there's the issue. When you did the next calculation, what did you do?
I did,
498 divided by
yeah.
what? That entire thing? That should have come out to the exact same answer, the 30.4. Right. Where you might run into an issue is if you look at that number and you go, oh man, that's way too many numbers, and we now decide to just divide it by 16.3. You've now rounded before the end of your calculation. That's going to get you run into a rounding error. You can only round at the end of the calculation, never before that. So in a lot of the scientific fancy graphing calculators, it'll carry the calculation for you. So it carries those sig fig, or all of the digits, so you don't have to worry about rounding until you get to the final answer. If you have a simpler, that was a right word, a simpler, more simple, it's got to be a more simple calculator, you may actually have to carry all those numbers and write them all down, which can be obnoxious. So graphing is easier. Yes? No? Okay. Other questions on this guy? Okay. What happens if we have an irregularly shaped object? All right. So we got a couple weird shapes floating up here. How can we calculate the volume or even area of those objects easily?
Is that bull farting?
It's art, man. Don't look at me. So we could look at the weird jaggedy shape on the left and probably come up with some approximation with all the different shapes in it and break that down, add up all those volumes. As soon as we go into 3 dimensions, that's going to become a little bit more difficult. We could melt this thing down, turn it into a cube, and then measure all the sides of the cube, and then determine its volume. Right? That destroys whatever object we have. But we could at least do that. What happens if we're trying to measure the volume of gas? That becomes a lot trickier. So we need to come up with other ways that we can measure these volumes, right, without having regular shapes. So then the question becomes is how? So there's a couple things we want to get through first. I saw some hands. So I think it's 1 and then 2.
No, I was going to tell you simpler is a word.
Sweet. Simpler is a word. There we go. Scrabble it up. What's your question?
I thought you were talking about the entire sculpture itself.
We could do that too. That's going to be probably equally difficult with all of those shapes.
Well, since gas takes the form of the objects around it, you just take the value.
But which gas are you measuring? So particularly for that bowl, if we're trying to get the gas that it released, what are we going to measure the volume of? The entire room where that bowl released that gas? There was already gas in that room. So we'd have to somehow subtract that out of it. We run into issues with calculating those volumes. So we need to come up with some other way to do that. So what we can do is look at a displacement. We can add these irregularly shaped objects into water. Right? They will displace the water, and that displacement in volume allows us to calculate or determine what the volume of the object was. So it's a nice little kind of sneaky way to go through and do this. And this is what, I don't know if it actually is Archimedes, that's why I said Mike's history, but I think he's credited for it. Dropping in the crown into a container of water and measuring the volume displacement. Use that information later to do some other stuff that we don't really care about at this point, but we'll see in a little bit. So that volume displacement allows us to do some interpretation, and we can now figure out the volume of the object. So in this case, we've got that green jade sample, very irregularly shaped. What is its volume? How did you do that? You need to give me a little bit more than looked at it. Okay, so you're saying 50 milliliters in the cylinder, so I can write that down. And I'll write down 5.0 milliliters. Why not just 5.0? The instrument tells me it's 50.0. Those zeros are significant because the instrument's telling me that. I can't just delete them. Okay, so you have to keep them. Okay, so I got that 50.0. What else were you telling me?
Well, when you drop that green jade sample in there,
Yeah?
the water goes up to 60.5 milliliters.
Okay.
So use and then use 60.5 minus 50.
Well, that's interesting, but you told me 50.0 first.
Well, that's how much water you started with.
So how do we calculate a difference?
Subtract the smaller one from the bigger one.
That's what we got to watch out for. It's not small one from the bigger one. It's never that, actually.
You have a negative volume?
It has to do with the difference. So we can't have a negative volume in this case, okay? But it has to do with doing these types of calculations for other things, because we could do a difference in temperature, and we can have a negative difference in temperature. Go ahead, yeah? Okay, we could say new minus original. Original. Our science fancy way. Final minus initial. Okay. New and original actually sounds kind of cooler, but it's the same thing. What's that? So you typically see these things. There, I think you're thinking physics. Is that where you pulled that one from? Physics, you may have seen xi or xf. Xi for initial distance, right? And then xf is final distance. Final minus initial. So whenever you calculate a difference, or really a change, it's always final minus initial. The symbol used to represent this is a delta, which is representing our change. So in this case, our change in volume is 60.5 minus the 50.0, and we end up with 10.5 milliliters. We now have the volume of our jade sample. Make sense? Okay. The other thing we could go through and do, which your textbook kind of addresses, and I get a little bit irritated with this picture, but it works. Might have to look to your left. We get a slightly better image on that. We've got a container where there's some junk down in here, and we're heating that stuff up. That stuff now reacts. Okay? And in that reaction, what it's producing is a gas. That gas then travels up here. If I want to know the volume of that gas, I need to have some way to control where that gas goes. So I want to do some kind of volume by displacement. So what I can do is trap that gas and watch how the volume of water changes. So as I form that gas, it starts to fill up in here, which then means what happens inside this container? The pressure builds, okay, which does two things. It either explodes the container, which is usually not a good thing, okay, or it pushes on the movable object. What's our movable object? The water. The water then gets pushed down and out into a container, and that outside container usually has markings on the side of it. So what I can do is measure the initial volume of that container and the final volume. I now have an idea of how much gas was produced based on volume in this reaction. Okay, kind of a neat little process. So we can look at even measuring our volumes of gases through water displacement. There's kind of an issue with this drawing, though, that bugs me a little bit. You ever taken a balloon and heated it up? Okay, and heat it up carefully. Nobody's done this? You take a balloon and you heat it up?
I've set it on fire.
Really? Nobody? Well, that, what can I do? Hot air balloons?
Okay.
What happens with the hot air balloon? You got a nice flat little balloon and you heat it up, what happens? It expands.
Sure.
Our volume expands. What happens if I add heat? And this is all now trapped gas. What am I doing to that gas?
Expanding it.
Expanding it. What is the heating process on its own going to do? Expand this, which causes the liquid to move down here and up and change the volume. So what am I actually recording? I'm recording two contributions. I'm recording a change in volume due to the temperature change and a change in volume due to the reaction. So we have to be very careful with our setups to make sure that we don't have these kind of secondary issues popping up. Okay? Kind of a neat process to think about.
How would you prevent that?
What you would want to do is expand the distance between where you're heating, where you're running the reaction, to everything else. So that by the time you get to where you're measuring the volume, the temperature does not change. Right? So that your temperature change is local within that reaction test tube, never makes it into the volume measuring area, and I don't have to worry about it. Which is one of the things that can be frustrating. Because if we ran this experiment and we saw this large volume change, we go, oh, wow, it produced this much gas. And then somebody comes along and tries to do it again and say, well, I don't get that same result. Well, maybe their result was because they used a slightly longer tube, which then does what to the heat effect? Reduces the heat effect. And so we end up coming up with different analyses for the exact same experiment, because I didn't think that that variable was going to become important. This would be ultimately one of those failures. Until we can find out what variables are important to control, we're kind of up in the dark and just keep testing until we can get a consistent result. Okay? Now we get density. Which weighs more, a pound of lead or a pound of feathers? Okay, this is always a fun little one to throw at little kids, because you can then point and laugh and make fun of them. Okay? Both of them will weigh the same. They're both a pound. Okay? But the natural instinct is we go, oh, the pound of lead weighs more. Okay? Not really. They're both a pound. Okay? They're both that mass. So why do we have this kind of instinct to switch the other direction? Well, one of the kind of psychological arguments has to do with density. That we think of lead as this big, heavy object, and we think of feathers as being this big, light thing. Well, when we're thinking of that, what we're really doing is doing a comparison of mass to volume. And it's that calculation that we're internalizing that we tend to ignore this whole weight issue. Okay? So density does play an important role. Okay? So what is density? So it's the mass within an individual volume. So if I wanted to look at a unit for density, what would be a good unit potentially? That's a trickier question. Starting to get to it. We just said density was defined as a mass with respect to a volume. Oh, geez. Let's just make that a dot. Right? What would be a unit for density? Grams. Square inch, really? Per milliliter, I heard, was an option. Why grams? What is grams? It's a mass. It's a unit for mass. What is milliliters? A unit for volume. Okay, so our density unit is a complex unit. It's a combination of both our mass and volume units. Okay? We can use this the exact same way that we use any other conversion factor. So I can now relate, say, 5 grams of feathers and turn that into a volume if I know its density. Kind of make sense? I think we maybe have some conversions here. No, we just got all that information. Okay, should we do a sample calculation?
Sure.
Sure, there we go. There's the excitement that we want.
Always just for you.
I need it. Without it, I just wither and die.
Yeah, don't
I lose my feathers. Wings. I meant wings.
I was gonna say, I don't know where you hide your feathers.
Because I'm an angel. Feathers. I'll keep digging.
You're just too great. We can't perceive your wings
So-
because of our lesser creatures.
We're looking at, let's say, 0.123 grams per milliliter. What is the volume? Oh, let's be obnoxious. Why not? Volume in liters. Doubly obnoxious. I'll spell it out. Ooh, triply obnoxious. British. Liters. For 5 grams of feathers.
What is the color?
So I want to know a volume. We'll do some of the setup here for you. We want an equals. I want liters. Starting with grams. And officially we really need to tag that feathers in there too. And 5 grams. You got questions? We got the setup here. I already started to do some work. Ideally, we would say grams, liters. Are those the same unit? No. So I got to do a conversion. Don't have a choice. Got to do it. So really what I want is I want a relationship between grams and liters. Do I have a relationship between grams and liters? No. Okay, so now I'm kind of up at a point where I can choose whatever I want to do here. If I want to start to convert liters into milliliters, or if I want to continue with my gram tangent. For me personally, I want to get rid of that gram unit. Okay, so I'm going to focus on canceling that gram unit, and I'm going to do whatever conversion I can to whatever unit is possible, and then I'll work from there, because I know grams has to disappear. So I need grams in the denominator. So now the question is, do I have a relationship between grams and anything else? I do have a relationship to milliliters. That's what the density is. And we've talked about this kind of in passing as well. We've got this stupid slash notation. Why do we have the slash notation? Typewriters. That's why we have that slash notation. Because it is too difficult to write these two numbers one on top of the other. We turn it into a single line. That's why we have it, because of typewriters, or ultimately even computers. Eventually that'll start to get phased out, and we'll always write it in a format that makes sense. What is that format that makes sense? 0.123 showed up in front of what unit? Grams. Per milliliter, and why is it 1? If it was any other number, does it equal 0.123? No, it must be 1. I now have a relationship between grams and milliliters. Okay, with that relationship, I will now go back down to my question. What number shows up in front of milliliters? 1. What number shows up in front of grams? There's no bottom or top. If you stick with the bottom or top notation, you may very easily say, well, I just got to multiply. No, you don't. The units tell you right away you do not want to multiply those numbers. Okay? That's why we set up this notation. What happens to our units now? Grams cancels, and we now have milliliters. Is milliliters equal to liters? No, so what do I have to do? I have to convert it. Do I know a conversion between milliliters and liters? Yes, this is one you're responsible for. Milli means 10 to the minus 3. And we now have our calculation. So we can take 5 times 10 to the minus 3, 0.123 times 1, and then divide numerator and denominator. Yes.
Does 10 to the minus 3 always go to the one that you're trying to get?
So this is where we have to be careful. Okay? And it's all going to come from what you guys have been working on. What we talked about before when we're looking at our powers of 10 and our prefixes. Okay? Our powers of 10 will always affect the base unit. What does milli mean? 10 to the minus 3. It's what I've told you in our sheets to memorize. The 10 to the minus 3 always affects the base unit. It needs to go up in front of liters. Okay. Liters is my base unit. Okay, my unadjusted unit by a prefix.
What if you were trying to go from milliliters to
Okay, let's not make that just an arbitrary thing. You said, let's go, we want to go from liters, 1 liter, 2 liters, to milliliters. What unit shows up on the bottom? What unit shows up on top? What does milli mean? 10 to the minus 3. 10 to the minus 3 affects what? The base unit. What's our base unit? Liters.
What if you weren't trying to find the base, or you weren't working with the base, so you were working...
Then you're doing a different conversion. That would be like grams and milliliters. Okay. So the powers of 10 are only going to be dealing with your base units. Okay. The powers of 10 are designed just for the base units and those prefixes. You're adjusting some base unit. Okay. And it's depending on how you've decided to memorize what that prefix means, on how you interpret where you put that power of 10. I'm telling you right now, if you follow the way we've been talking about it, milli means 10 to the minus 3. It affects the base unit every time. Okay? What does centi mean? 10 to the minus 2. Where's that 10 to the minus 2 going to show up? Base unit. It will never show up in front of your prefix unit. It's all about that base. Okay? Questions? I don't know what the answer is. I started that whole thing off. Don't ask me to calculate that. What's that? Okay, wait a sec, wait. Because I have a feeling you're asking about sig figs. 0 point, or I'm getting too much noise. 0.0407. That's it? Okay, so there are enough questions about sig figs and calculating this that we need to go through and address this appropriately. Okay, so let's take a look at our answer. In theory, the answer, if you follow this calculation, is 0.0407. Yes or no?
Yes, but no.
I will accept a yes. Okay, as far as what the calculator spits out. Now the part is what would we do with our sig figs? Okay. This is why I don't do problems on the fly, because I don't treat sig figs with enough respect. Okay. If we look at this question, what are our sig figs? 1, because of which number? The 5. So the answer that we would need to report, according to that, would be 0.04 liters. Okay? There is only one sig fig that I can include. I can look at the first insignificant digit in that case, which would be 0. What's its relationship to 5? Less than 5, so I keep it just as 0.04. Yes?
And on the test, you said we'll only know if it's a significant figure question by the answers you're giving us to choose from.
On the test, when it comes to significant figure questions, it is usually explicitly stated, include sig figs. Okay. I think I can make it bold if you send me an email to remind me. I'm pretty sure I can do that. That doesn't work. So let's address another thing here. When it comes to the exams during the semester, I've got no problem supplying some extra information here and there, okay, and telling you sig figs, putting it in bold, addressing other things. I would also highly, highly, highly recommend you read through my old exams. They're really helpful. They have some information in them that if you don't read through them until the day of the exam, you may be missing something. Okay? So please, these exams are on Canvas. Files/old exams. Those of you that have already read through them are more than welcome to share with the rest of the class at any point after class. Okay? But there are Easter eggs, if you will, within my exams. The final exam is not written by me. You lose all of those Easter eggs, so take advantage of them during my exam so you don't worry about it when it hits to the final. That also says when I go through and bold things in the regular exam saying watch out for sig figs, that information does not show up in the final. Okay? So be aware of that when it approaches that time. Other questions? Relatively confident with this question, fun thing that we threw up here? Yeah. You guys made me make up on the fly. Right. So really, density is just a new conversion factor. I think I've already said this. 151 and 152 are all about conversion factors. Guess what 150 or 130 is all about? Conversion factors. Everything we do when it comes to math is conversion factors. We may hide it very, oh no, it's density. It's a load of crap. It's conversion factors. Okay? Everything is conversions. You need to pick up a pattern on how to go through and solve these so that you can solve them consistently. That's what dimensional analysis is going to do for us. Okay? Units for density. We already picked out 1, grams per milliliter, but there may be times where we don't want to use grams per milliliter. Why not? Because if we look at the number associated with grams per milliliter, it may be too large or too small for an individual reasonably sized object for us to look at. So we may change the units that we want to work with. For instance, if we look at the density for ice or water, grams and milliliters actually works out pretty well. But if we look at the density for a gas, the density now becomes such a small number, Okay, we're probably pushing into some fractional numbers here. You're getting something like 0.00123. I'm really creative today. Okay, grams per milliliter. We don't like all those zeros. So what we can do is change the unit. Instead of it being milliliters, we may say liters. Okay? Or we may say kilograms. So we can change those units so that the number associated with our density isn't as nasty looking. Okay? Kind of makes sense? So be aware, density is just a relationship between mass and volume. We can use any units we want, because what can we do with any of those units? We can convert them to any other unit. So we tend to pick units for each of our phases that make sense for that particular phase. Okay? Where we can actually test on the subject matter of density is what can we do with densities. So what we've got is a graduated cylinder on the left with, if I count right, 6 different substances in it. Okay, those 6 different substances are related via how?
They all have a density.
They all have a density. Good call. Let's go a little bit more with that. They all have the same density. They're different densities because they're moving to different heights within that cylinder. What can you tell me about the density of L1? The very top one right there. It has the lowest density, which means it's going to sit at the top. So in an individual mass per volume, its mass is relatively small. What can you tell me about S3? It has a very high density. That meant when we put that high density object on top of liquid 1, there's so much mass in that space, it immediately falls through. Okay? And it's going to settle to a point where it now equilibrates against whatever's around it. Okay? So we can now rank these things based on their densities. S2. Higher density or lower density than L1? Higher density. Why? It's lower than it. Okay. S2 relative to L2. Why lower density? Because it's above L2. S2 has a lower density than L2, which is why it sits on the surface. It doesn't drop into it. What is the density comparison between? Any guesses? No, I don't think that one's that hard. S2 and water. S2 is more dense because it is settled to the bottom of our water layer. How would you know that they were the same? Sitting right in the middle of it. Okay. Not easy to do because if I dropped it in, it's got gravity, it's probably going to fall all the way down. Okay. And if I just put it in gently on the surface, if it's got the same density, what's it going to do? It's just going to stay there. So if I want to see it where it has the exact same density, I'm going to actually have to put it into the liquid all the way and then very carefully move away from it without moving it. And it should stay in that exact same position. Okay? Questions about density? Don't look too excited. Oh, man. Okay, well, I gave you a problem. Go ahead and work it. Some people don't, so we'll work through it nice and slowly. What is density? Density equals mass divided by volume. Let's ignore the units for the moment because we don't have a density, so we need to find a density first. Do we have a mass? What is our mass?
224.50 grams.
Do we have a volume? What's our volume?
10.07 meters cubed.
What happens with the units? What would I get for my units at the end of this?
Grams per centimeters cubed.
Grams per centimeter cubed. What's the very first calculation you're asked to do?
Gram.
All you got to do, take the mass, divide it by the volume. There's nothing else to that first part. Okay? It's based off of the definition of what that term is. Where I think people might be starting to jump to is then try and do the next part before you finish the first part. Finish the first part. Get the density, get that calculation down, get it written. Okay? Second part. What do we want for an answer? Pounds per liters. What information are we given to start with? Grams and centimeters cubed. Where do I want the grams to show up? Numerator or denominator? Why do I want grams in my numerator? Grams are a measurement of mass. If we look at our answer, where's our measurement of mass? In the numerator. So my grams that I'm going to start the whole calculation with need to still be in the numerator. Okay. Now it's up to you on where you want to go with this. I've noticed most people then also realize that what we're trying to do is solve for a density. So let's start with a density. How do we calculate our density? It's mass divided by our volume. 10.0? Yeah. We now still have this complex unit. We start with a complex unit. We're going to end with a complex unit. We aren't simplifying at any point all the way through this. Which unit do you want to mess with first? I would mess with that one first too. Grams, and I want to turn them into pounds. Do I have a conversion factor between those two? What is that conversion factor? 1 pound is 454 grams. Where does the 1 show up? In front of pounds. Where does the 454 show up? Okay. What happens with my units? Grams cancel. I now have pounds per centimeter cubed. Not too bad, actually. I got pounds. I'm getting closer to my answer. What do I need to do now? I need to get rid of centimeters cubed. Where does centimeters cubed show up in my calculation? In the denominator. How do I get rid of it? It needs to now show up in the numerator. What do I want to show up in the denominator?
Liters.
Liters is ideally what I'd want to hear, but here's our issue. Do we have a conversion between centimeters cubed and liters? No. So what do? Change it to milliliters. Do I have a conversion for that? What is that conversion? What units am I in now? I kind of understand your statement of milliliters. It's not in milliliters, though. It's in pounds per milliliter. So the milliliters is in our denominator. What's our last conversion need to be? Milliliters to liters. Where does milliliters need to show up? Y in the numerator. So it cancels with our previous one. Where do liters need to show up? In the bottom, or a denominator, because that's where it needs to show up in our final answer. Our milliliters can cancel. We'd end up with our correct units. What's our conversion between milliliters and liters? 10 to the minus 3 liters, 1 milliliter. Questions? Yes.
So why is it different to, like I started with 22.45 grams per 1 cubic centimeter.
Is it a different calculation?
That's what I'm asking.
Okay. What is 224.5 divided by 10? Exactly the number that you just listed out to me. The calculation has already been folded into it. I don't need to worry about what number I start with. If you chose to start with grams per centimeter cubed, then you're fine with that. If you did not start with grams per centimeter cubed, you could still do it here. All right? That information is still folded into our answer. Okay, we ready for the next fun question? Which is going to be sig figs. How many sig figs should show up in our answer? Let's start over here. How many sig figs? Why is that infinite? It's exact, metric to metric. Say that a little louder. Infinite again. That is an exact metric to metric conversion. Next one. Got a dodge on that one. That is not infinite according to our table. All right, that would have to come out of our textbook and we look at that. That's not a direct conversion. That is 3 sig figs.
Wait, the one to 454 is not?
Is not an exact.
Stated that it is.
What I stated was the numbers that came out of your book. The numbers that came out of your book are not an exact measurement.
What if the book is telling us?
If the book tells you that that's infinite, then you can say it's infinite. The book does not tell you it's infinite. You pull up, I'm 90% certain on that. You pull up the book on that chapter, it does not say it's infinite. It says they're 3 sig figs. The only one that's infinite is the inch to centimeter, not grams to pounds.
What if all of your conversions are infinite? What would your end answer become?
Infinite sig figs.
How do you write that? You just keep writing numbers till you die? I mean,
Yep, you would. So would we ask that question?
No.
No, we can't possibly ask that question because you don't have the space to write all those numbers. So that question would never get asked with infinite sig figs all the way through. Okay, it can't happen. Okay. Very beginning, what do we got? This one's a bit tricky because we had 2 numbers associated here. So we'll do numerator and denominator. Numerator has, I heard a 3. Numerator is the top one. Has how many sig figs? 4 sig figs. I just want to make sure that we're on the same wavelength there. Bottom has 1, 2, 3 sig figs. That last 0 counts because I have a decimal point, which means all I need is a significant digit in front of it. I don't know with that 0, so we look, does it have a significant digit in front of it? Yes, 3 sig figs. Run that by me again.
You have 2 numbers and you're trying to find the sig figs. You take the lowest or the highest.
When you're doing sig figs, it's and multiplication division, it's the fewest number of sig figs. So in this calculation, how many sig figs need to show up in our answer? 3. For multiple reasons. 1, because our conversion factor had 3 sig figs, and 2, because our volume had 3 sig figs. Okay. If our volume had been given to 5 sig figs, or even 4 sig figs, our answer still needs to come out to 3 sig figs because of that conversion. This is one of those cases that I talked about before. If you run through and you took a measurement that had 5 sig figs, but your conversion only has 3, don't use that conversion factor. Find a conversion factor that has at least that 5 sig figs. Okay? Because you don't want your conversion to ruin the data that you collected. So our answer, theoretically, assuming I did it right in the upper right-hand corner, we would have 49.4 pounds per liter. Everybody get that?
What if you had addition and subtraction?
If we have addition, subtraction, are the rules the same as multiplication, division? No. What changes with addition, subtraction? If you have both, you have to calculate each independent of each other. So if we had an addition and then a multiplication, we look at the sig figs from the addition, get a number. How many sig figs should we carry? If it says 2, but our multiplication, or the next number has 3, we still can only carry 2.
So in that question, there's a 0 after the gram, so is that not a significant 0?
Oh, I didn't see that. Oh, that was kind of accidental. So if I can get your attention real quickly, good point was made here. So one of the reasons why I'm not super strict with sig figs. If we look at the mass to begin with, it was 224.50, which meant there's another 0 there, which meant our sig figs was not 3 still, but it also was not 4. It was 5 sig figs because of that extra 0. Thank you for pointing that out. I missed that. Okay. Yay, sig figs. Questions?
Would the top problem then have 3 sig figs as well?
The answer to the top would have 3 sig figs as well because of the 10.0. Pretty sure we've beaten density to death. So what I would like you to do is try this one at home. Okay, and if you've got questions about it, ask. Let's see, does the answer pop up? I don't have an answer on it. Okay, so what I think I'm going to end up doing is actually finishing chapter whatever we're in, 2. And then that will leave Tuesday as pretty much an open field day for questions. Okay, so if you've got any questions about the practice exams or anything else, you can take a look at that. Get your picture? Thursday? The exam is Thursday. So Tuesday, because we should get darn close at least to finishing the rest of chapter 2, Tuesday will be mostly just review. All right? So, last 2 sections in chapter 2 talk about temperature and heat. So temperature is a measure of the average energy within an individual sample. So if we take a look at a beaker, we can measure the temperature of it. And that's a representation of the total energy within that thing, within that container. Okay, or a way for us to kind of understand it. We have special units that are associated with temperature. In the US, we've picked Fahrenheit. I don't know the history on that. Wow, excuse me. I don't know the history on Fahrenheit. Okay? We also have Celsius. It also happens to be the most widely used temperature conversion or temperature unit is Celsius. Last one we've got in particular science fields, we've got kelvins. Kelvin is an absolute temperature scale, which means when we go to report Kelvin, the unit that we use is merely K. But if we use Celsius, our unit is degrees C. So that degree is kind of a relationship thing that does not show up in Kelvin. Right? And that's because Kelvin is absolute. The degrees shows up for our Celsius and for our Fahrenheit because they are not absolute. Okay? So those will be our symbols for those. Of course, with new units, what do we then have to do?
New conversion.
Yay, new conversions. Okay? But thankfully, they're powers of 10 conversions, right? Except not at all. Not at all close to powers of 10 conversions.
If you're going to be lazy, why isn't there just one?
So, we do run into this issue of why did science break out and have all these stupid conversions and all these different units, and why do we deal with this? Remember, 800 years old. 800 years ago, we didn't have the instant communication. So somebody in the US came up with some way to represent temperature. It probably wasn't in the US 800 years ago. Somebody in Germany came up with it. Somebody in Italy came up with it. Somebody in France came up with it. Okay? Somebody in China came up with their unit system. Those unit systems, then when we started to communicate, didn't mesh. So we had to come up with some way to talk to somebody else about those unit systems. Well, why didn't one country or person say, fine, you're right, your unit's better than mine. Let's use yours. Because think about, it's not even just scientists, think about any field you want. When do you get anybody saying, fine, you're right? Okay? The only time that happens is when they're pissed off in an argument and they don't want to talk to you anymore. Okay? We all have massive egos, and nobody's going to step away and say, I can accept your point of view, let's work with yours because we can work with that. It's a feature of how it was set up. Okay? So yes, we've got all sorts of messy units, and as we continue through, we'll keep encountering more and more and more just nasty, stupid units. Okay? We just kind of have to deal with that. So within these scales, we've got some basic systems specified here. I will note that this is a bit confusing. That is not freezing at negative 273 Kelvin or boiling at negative 373. They're supposed to be colons, not dashes. Okay. Exactly right. There is no negative in Kelvin. That's why it's confusing, because those look like negatives. So those are all positive values. Okay. The reason why we shifted to kelvins was ultimately because we realized that negative signs are a pain to work with. So we ignore negatives, or we came up with a system to get rid of the negative sign, because negative signs confuse the heck out of all calculations. Yes, and then we'll end. That was actually a typo that I made a while ago. I haven't gone back to fix it, but it should not have the degree. Oh, man. God, fine. Just pick on me. Okay. Conversion factors. We got our conversion factors up here. And hey, look, I fixed it here. We don't have the degrees Kelvin here. These are our conversion factors to get back and forth between each of these. Okay? You are expected to memorize the Kelvin one. Why the Kelvin one?
Science.
Fair answer. I didn't consider that. It is science, but really what I was going with that one is it's also really easy. 273. Add 273 to whatever your degree Celsius is, you're in your kelvins.
Just 273 or 273.15?
How many sig figs do we typically carry in our calculations? 3 sig figs. Every so often, you'll find that I have some random sequence of numbers memorized. Guess which sequence of numbers I happen to have memorized? No, I don't have pi. I have our Kelvin conversion, 273.15. Okay, so that's why that was there, because when I wrote it out, that's just what I remembered. Okay? The other ones are not so nice. I will provide you the top one. You get to do the second one. Okay? Absolutely, I will ask that question. What is the relationship between those two conversions? Algebra. That's it. Okay? And I know everybody loves algebra, but that is it. Okay? You are expected to do a minimal amount of algebra. If you've got questions on that conversion, talk to me. I can help you through with that. All right? We are done, so I will go ahead and stop.